adjust your life or your curriculum in courses. You can fill in the gap, check the online course, and always try do by yourself. Okay? Try to understand by yourself. Okay? If you don't understand, or if you just follow, like you have questions and solutions, if you just follow the solution without understand the concept, I think uh, it will be not good for the future. Okay. Okay. Let me start with the review. Uh, Last time, this is our um, example. I will give one more example to give you a better understanding how to optimize problem and how to find models and how to simplify the models. Okay. Okay. Find the point Okay, you have the question is the hyperbola. Okay, so find the point on hyperbola xy equal 8 that is closest to point 30. Okay, so as a review, okay, I will write necessary things that you need um, to do. Okay, so first draw the diagram. Maybe if you want to name the variables. If not, then just draw the diagram. I think that's just fine. And then find a relation or model. And you have the constraint and you have the optimization. Our goal here, we need to find the distance, right? The distance that is closest to 0.30 from the parabola xy equal 8. If you're wondering how you can draw, you can just use the uh, y equal 8 over x. Try several x and you will have a curve. Okay? You have a curve. Okay? You can draw roughly, and you can draw the line from 3.0 to the hyperbola. Okay? So I think our hyperbola will be our constraint. And our optimization will be the distance. The distance. Let me draw the illustrations. Okay, maybe like that. Okay, and it will be going around. Okay, this is the hyperbola. Uh, y is 8 over x. And then our point 3 is here. So from this 3 here, you have a lot of choices, right? You can move here, here, but finding the closest one, right? Let me just make, I think around here, maybe that will be the closest. Remember, this is just a diagram, just illustrations, okay? We need to confirm with our calculations later. So let's try make a distance here. Let's say this is d, okay, the distance. And of course, if I make a line D here, at this point, I will have another number here. Let's just say A, okay? Let's just say A. Let's just say A, and then this is FA. Or if you want to directly go 8 over A, okay? Okay, now the distance, how to find this distance, we can, if you forget how the formula is, you can think like a triangle here. This squared plus this squared is this squared, right? You can use that. So I will have d squared is, this is a, so this will be a minus 3, right? So a minus 3 plus 8 over a. So our d will be, okay, and this will be our optimizations, right? But now the question is, which one do you think easiest to be differentiated, easy to be derived? This or this one, right? So because there's nothing wrong about the square root, there is nothing, there's no restrictions. We can use this model instead of it for the easiest derivative, right? So let's say we are using these models here, okay, to simplify our calculation. So this will be our optimization. And let me write, okay, so let d squared, let's say with another symbol, okay, let's say it's s, okay, so that it's s is this equation. So we can derive this, okay, so 2a minus 3 should be squared, should be 64 multiplied by 2, right? So it'd be negative 1 to 8 over a cube, right? And then this should be equal to 0. 2a minus 6 and again, to simplify, you can solve this if you want, but if you think you need to simplify this, then let's just multiply all by a cube. So divide by 2 and multiply by a cube. This will be a 4. And you can check the polynomial. Okay? You can use the polynomial division or synthetic division, checking the roots for the fourth degree. Let's say the factor of 64 is plus minus 1. It's 4, 16. Yeah, only 8, right? Yeah, there's a lot. Now, we can check the, I think at least it will have one positive 0 and one negative 0. So let's check the positive. You can see positive 1, if you plug in, not possible, right? Positive 2, you check 2, 4, 16, 8, 3, 24, 24 minus, and not possible. How about positive 4? 4, 4, what? 16, 16, 2, 5, 6, 6, 6, 6. I think 4 may be possible. Let me. Uh, 4, 4, 4. Oh, wait, wait, wait. This should be 0, 0. Yeah, at least we get 4. So a minus 4. Um, so at least it's 4. But I believe the other roots will be, I think, imaginary. So at 4, 2, and 3, 0 will be closest distance. And you can check the D will be 4 minus 3 is 1 plus 4, 8, 4, 2 squared. So 1 plus 4 is 5. So D is 5, square root of 5. Okay. Okay, this is just a review for the. Okay, is it clear now? Okay, thank you, thank you. Okay, so the point here that I want to show you is instead having only D as your square root, it would be better if you just derive from the D squared. Okay, so you might have choices when you are dealing with the optimization. You can deal the optimization as D itself or D squared. Okay, my suggestion is just deal with the D squared because it's easy to be derived. Okay, you will also find another another case that's similar that you need to simplify the models, but without any simplification, actually you can also derive this and solve the problem. But maybe it will take a longer time. Okay, as long as is it that is correct and makes sense. Okay, that is something that you can do. Okay, okay, and also to remind you that all of my questions in exam usually it will have not really long answers, so it will be short and the number should be not difficult. So maybe if you find in my exam something that weird, the numbers going large or have more decimals, then probably you have going to the wrong way. Okay, that's my suggestion. Because I want to find numbers or solution that not really that long, and it should be able to solve in particular time. Okay, okay, that's just the review of the optimizations. Now, actually, I want to go back a little bit. Okay, uh, additional notes for the Newton's method. Okay, just a little. Okay, for addition, I forgot to mention. So after you find optimization, find the first derivative, make it equal 0, and uh, check the critical point. And that's it. So most of the case, you will get the maximum or minimum value. Okay, let me go back to some notes. Okay, additional notes for Newton's method. Because from here, I will relate to linear approximation and I will relate to integrations, okay, so to make it easier. Okay, what's the deal with Newton's method? The purpose is to find real roots with approximation using the tangent line. The same tangent line you are using with the linear equations and linear approximations. Okay. And let's start with the some graphs. Okay. Okay, let's start with, I will approach the roots, okay, in the x-axis here, right, of the function. I will approach from maybe around here to give you idea, and we can review our Newton's method. So let's say this is the x0 or x0. Approach until this point in the functions, and then I will approach and cut the x-axis with the tangent line from this point. Okay? Okay, that's my tangent line, and I will get the second x, which is the x1. Okay, this. Okay. Now we remember, or if you don't remember, you just remember the line equations. Okay? The line equations start with this, right? Let's say dy is our f of x. Dy1 is the, let's say, f of some a, and then plus the gradient is actually the f prime at the a, and then x. We can say this is delta, or just x minus x1. Okay. The idea of the Newton's method is, because you want to have the intercept here at y0, then make the fx 0. Okay, make fx 0, and we need to find the x. Okay, make 0. And we can simplify this, become and we can exchange this x1, a with all the information from here. Let's say we are looking for the x1. Okay, so let maybe change here. Okay, change the a. This is, let's say this is x0, then x1 minus x0. And this will be our approximations. So our x1 will be x0 minus this ratio of f and f prime at x0. Okay. So linear approximations, tangent line equations in general, it's actually the same cases with the Newton's method. So if you forget what Newton's method is, remember the linear approximation or tangent line, and make the fx0, and maybe you can derive the formula by yourself. Okay. And to illustrate how the tangent line cut the x-axis, you can see from here. Okay, let's start from this x0. We get the tangent line. We cut the x-axis. We get the another x. Okay. If we want to, let's say, use the x1 to check another x2, we can do that. Bring the x1, go to the functions, and cut another tangent line. Okay, let's do one more and see. Okay, let's say that is our tangent line. Let's say this is x2. And the more iterations, okay, the more we do from x0, then we get x1, and then we get x2. Maybe from x2, we can get closer and closer to our roots here. Okay, so if imagine, okay, if the functions is really a complicated function, and maybe you know that, oh, maybe it's near some numbers, you can use the numbers inside this computations, and you can do maybe 2, 3 times, and then you get, oh, it's getting closer to some numbers in decimals. Okay, and that's the idea for, I think, for computations, iterations, some software, they will use this kind of logic, okay, to get the roots, and it will be repeatable. So this x1, the next one is x2, this is x1, and then all change to x1. And if you need more, x3, it become x2, x2. Okay, I think that should be make sense, right? So you will have from here you will have iterations or repetition, and also you can find error. You can find error. So error, you can find error from let's say the x. You can find error also x. And maybe the closer you get, the error maybe it will, maybe at the beginning, maybe it will be like around 0.001, and maybe the second iteration will be 0.00001, and it will increasing more and more the decimals, meaning the roots is closer and closer. Okay, so you can check also the error if you want. Okay, if you have analysis, okay, maybe later when you have data set problem, you want to analyze, you can check the error. Okay, some notes about the Newton's method. I will write in the next page. I hope these iterations you get the idea about this iteration. Okay. Uh, Let me write Newton's method. Um, it works very well if, okay, if the absolute value of the f prime not small, and the f double prime not too big, and the point x0 starts nearby the real roots. Okay, the real roots. Okay, now how Newton's method fail? Let's say we have that graph, and then it starts to fail if you choose maybe the x0 here. And you get the tangent line like that. Maybe not really that good. Okay. I'm modifying my functions. Okay, so you can see why it's fail. Okay, imagine you're choosing the wrong x0, and it's resulting. Maybe it's too far. Okay, maybe it's too far. Maybe the graph is not too clear, but what I did is I make this x0 and make the tangent line. It's too far from the function, and when it's too far, you will not get the another x1. Okay, you cannot approach more. Also, another fail will be you start from maybe here, the x0. Okay, and you get x1. And then you draw the tangent line from the x1. And then let's say this is actually, I need to make like that. Okay. So this means I'm starting from this x0. I get x1. And then I get back to the left side, x2. So it means it will be cycles. And you will be round and round, and you will not find these roots. Okay? So meaning this x0, the point that you need to choose is crucial. Okay? You need to find closer, but when you are cutting the x-axis with the tangent line, it should be make your next x1 closer and closer to the real roots. Okay, so this will be cycles. So maybe you will have x0 to x1, and then it will back to x0, and then you will going nowhere. Okay. Okay, I think that's it. The important point uh, for the Newton's method. Okay. Okay. Any questions? Okay. I leave the how to solve with certain problems with your TA. Okay. I hope your TA will give some Newton's method, because I think in textbook or any exercise, the Newton's method, the questions usually direct and not really having any definition or concept. The definition is just the iterations. Okay, just use the iterations. Okay. Okay, that's the Newton's method. Um, we will go to the next section. It should be the antiderivative, but I will start from uh, differentials. Okay, we need to look back at our linear approximations. So if you have x, and let's say we have x plus dx, or let's say this is not dx, let's say delta, and this is delta y. Let's think how linear approximation works. For example, okay, you want to let's say this is cube. You want to find 64.1 square cube. Then we can start by making y, making our functions x, right? And then we can find. But let me use dy. Okay, is 1/3 x negative 2 over 3 dx. Okay, these terms, okay, we call these terms differentials. Okay? So instead using the y prime or dy over dx or ddx of y, we can directly turn this y into dy and then derive the whole x here and make the x, okay, at the end. Okay? This is called differentials in terms. So at if we choose A64, then our FA will be 4, right? And our dy will be 1/3 of 64 dx. So this should be 1/3 and 1/16 dx, or 1 over 48 dx. And your this will be approximately our y plus dy, right? So our y will be the 4, and dy will be 1 over 48 dx. Dx is 64.1 minus 64 is 0.1. So it's 4 plus 1, 480. It's around 4.002. Okay. So now we are using linear approximations, but it's the same. But what I'm writing is I'm using the dx here. So let me write the notes here. So if y is equal f of x, dy is f prime x dx. So dy over dx, if you remember, this is the f prime x, right? So these terms here becomes important, and we call them differentials. So we are approaching these differentials to understand the next section, which is the antiderivative and integrations, okay, from here. So let's go to the next one. So integrations, okay, let me write integrations. We can approach with intuitively. We call this the antiderivative. And we can approach the integration through geometry. This is what we call later the Riemann sum. Okay. Now let's start from the antiderivative. So let me write the f. Okay. Let me write the notes for integrations. This is called the antiderivative of f. Or we can also say this is indefinite integral of f. To start with, we can first imagine some functions, okay, that we know how to derive, and let's make definition how to make backwards. Okay. So first, let's imagine this sine x. Of course, it will start with the cos, but derivative of cos is negative sine x, right? So we can define this as negative cos cos x plus c. Then if we want to trying to prove that intuitively, okay, I haven't mentioned any proving. So the f, or let's say the f prime, will be sine x. Well, let's start with the other functions that I think easy to follow first. Let's say this is x with power of n dx. So the idea of integrations, okay, before we are using any technique to integrate we start from any functions that you think easy to derive, and let's think backwards first. Okay. So the idea is you have d dx of something that make x with power of n. So because in derivative, you should have the minus 1, right? If you have x squared, you derive become 2x, right? The n becomes forward, and you need to minus 1. So if you have x squared, you have 2x. 2 minus 1, only 1. So before you need to have n plus 1, right? And to divide the two, we need the n plus 1 at bottom. Okay. So I can write here the integration. Okay. So I'm starting with something easy to follow. Okay. Intuitively easy to follow from our definition in derivative. Okay. We can think backwards. But this is not okay if n is equal -1, right? It will be the definition will be incorrect because it will be power 0, which means it will be 1, right? And then other functions that I think interesting and I think important also to note is 1 over x. So what functions that when you derive, it become 1 over x? Log, right? The natural log. So let me write this as n x plus c. And there is something special in this log. The correct way to write the ln x, okay, you need to have the absolute value. Okay. So you need to have the absolute value here. If we are trying to check this ls, we can check become ddx ln x and ddx ln -x. In which both ln x of course is become 1 over x. What derivative of ln -x? You bring down -x to downside, right? -x. Derivative of -x is -1, right? So it's the same 1 over x. Okay. That's why we need to have the absolute value, because you have two possibilities. Either the x is positive or negative. Not the numbers in ln, okay? The x. Because if negative, then it will be impossible, right? Okay. And here some graphs, okay? You see this is the ln -x. This is ln -x. This is ln x. And both have the same derivative. Okay. Another functions that we already discussed in derivative also we can review now is the secant squared x dx. So what is the functions when we derive become secant squared? Tangent, right? Tangent, right? Okay. So I'm reviewing some derivative and make some correlation with integration, and then later we can going forward to the proving the integration. And then the other I think this is common. Let's say the x here. So you have the 1 over 1 plus x squared. What functions? Okay. It's the inverse, right? The tangent inverse. Okay. I hope you still remember this tangent inverse, sine inverse, cos inverse. I mean, not remembering the formula, but remember how to get the valuations. Okay. Okay, some unique property of the antiderivative. If uh, if f prime g prime, then this difference in let me start with henge um, where c is constant. Okay. I think this is um, a good method to remember why in our integration we still have the constant c. Okay. I will later show you the examples. Okay, why we need the constant c. Okay, I will move to the geometrical approach now, and later back to the fundamental theorem of calculus. Uh, to start with, okay, so this is the geometrical approach. So the idea of integrations is to calculate the area under the curve. Okay. Remember that you have integral fx dx, right? So basically from differentials at the early courses, okay, so these differentials. So basically what the integrations tell us is if we have a curve like this one, okay, we have a curve, let's say the interval is from A to B. Okay, imagine you have rectangles, like a long rectangles, long box here, and you have a lot of them. So the area will be the total of this plus 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 plus, right? And you can check the area, the delta x multiply with the f of x, right? Depends the height of the function. It's the function itself, right? So I can write, let's write the fx I, okay? Because you can start with 1, 2, 3, any x that you can choose from here. Let's start just using the xi here and delta xi. And you need to sum, okay? You need to use the sigma notation, meaning you need to plus the first rectangle plus 2 plus 3 plus until some rectangles already been summed. Okay? And then let's say we are going for n rectangles, and I start from the I equal 1. It means start from the very beginning from our intervals in definitions. And imagine there's a lot of rectangles. So I will use the limit. Okay, I will use the limit as n approach infinity. And it will equal our integrations fx dx. If we observe AB, then this AB. And we call this the Riemann sum or Riemann integral. So the dx is the width, and the f of x will be the height. Okay. And also to note that notes, okay, the sum means the net area, okay, the net area. Meaning, if you have the functions is like this. This is A, this is B. So if you have this curve like this, meaning the Riemann sum is the net area, okay? So all above the x will be positive, and this will be negative, okay? So this negative, this positive, okay? Just a note to make sure. Okay. Okay. Now see these approximations. Okay. At least we have two. Okay. If we want to use the Riemann, let's see this graph here. We call this is the left endpoint. Okay. So the difference left and right is on the rectangle. Okay. You see the rectangle touch the curve, right? But only at the left side. And the conclusion, because you are using this left side, you see this is the curve, this area under the curve. Okay, let's say this is AB. Let me write AB. You see this small triangle here? It's a gap, right? It's like a hole, right? Here. meaning there is certain amount of hole or gap from the curve and the area approximations. Okay, we call that it's underestimations. Okay? It's underestimations. And how to make sure that our area getting closer to the correct area? How to make sure that we can make the number of rectangles more and more. Let's say we have this is 7 rectangles. Let's make 10, maybe 20, maybe 50. It will be much more smaller, and this gap will be smaller, right? And the error will be also getting smaller. Okay? The error will be smaller. But if we use this and we solve any hole here, we call this underestimate. Okay? This is a left endpoint. And the right endpoint, if we are using the same curve and we are using this different endpoint, it will touch the right side of the rectangles. Okay, and it will conclude this area above the curve, right? This area above the curve, and we say that this overestimate is over than we actually has under the curve. Okay, and we can make this smaller also with the lot of rectangles, and it will be smaller and smaller. And that is the right endpoint. Both left and right, you can use it to approximate, and depends on the functions actually. Okay, so not always the case that right endpoint always overestimate. Not always the case. It depends on the function. Depends on the function. But how you are using it will be different. Okay, will be different. The different will be the starting point when you are defined your delta x. Okay. So delta x here, right? So maybe this is 1, this is 2. Usually left and right, you will shift it the x at least 1 point, okay, if you are using the same curve. Okay. Okay, and also we have the midpoint approximation. So left, right, and we also have the midpoint. So instead using the left or right, we can use the midpoint. Let me write the midpoint rule. I will give you all the necessary theorem first, and then maybe we can have the examples later. The midpoint rule. So if you want to calculate the integrations fx dx from a to b, this approximate to the sum of and this is equal delta x. Okay. So do you familiar with the sigma? I forgot to ask. Do you familiar with sigma? Sigma, this is the sum notations, meaning you have a formula here, and you need to add the formula based on the point. This is start from 1, meaning x1 until some n, until n here, and this is the fx delta x is the formula. Okay, so you need to fx1 delta x plus fx2 delta x plus plus plus, and then until the very end. Okay. And for midpoint, the x will be defined by the half of Okay. This is if you have the a line above the x, meaning that's the midpoint. Okay. It's defined by xi minus 1 plus xi, meaning actually this, if you want to make sense this formula, this is the previous terms, this is the next terms. Okay. So x 2, 1, 1, 3, 2, 4, 3. Okay. So this will be the midpoint of these terms. And all the delta x, okay, the delta x, if I give you the delta x formula, let me write here some notes. Okay. So delta x is b minus a divided by n. Okay. This is the interval, and this is n rectangles. How many column you want to make? Okay. Just a notes. Okay, so left, right, midpoint. Another one, it will be, we call it trapezoidal. Let's say this is 1 and it's a 6. Let me zoom this out. So let's say this is our functions here. Trapezoidal means we are making not rectangles, but trapezoids. Okay. Okay. This is A, B, C. What is the area of this A, B, C? Remember? Trapezoid. A plus B times C over 2. Right. Okay. So let's say this is 2, 3, 4, 5. So the area is F1 plus F2. Okay. So if this is the f of x, right? And this will be the delta x. So F1 plus F2 divided by 2, and this is delta x, and plus, okay, F2 plus F3 divide 2, delta x plus, let's say we finish the last 5, 6 divided by 2 delta x. Let's factorize. You get the delta x divided by 2. You get f1 plus, okay, you have f2, f2, 2 f2, f3, and then 3, 3, 4, 4, 4, 5, right? And you get this pattern, okay? So the first term will, and the last term will have a constant 1, and the middle part will be 2, 2, 2, 2, okay? And it should be, n should be, this should be even, okay? Okay. I think we can go for some definitions and property. Let me start with this pretty long, but let me just start with the definition of definite integral. Okay, so basically, okay, definite integrals mean if you have integrations, you have fx dx, you are having definite interval. The definite integral means the interval. So for example, from a to b, that's we call the definite integral. So that means if we integrate this integration from a to b fx dx, we will get the exact area, okay, without any plus c, okay. Then the definitions. The definition we start from defining the delta x is b minus a over n. Okay, that's the first definition, and let this the first interval become the x0, and the last interval becomes b n xn, and then let's use the x1 with the asterisk as our sample points, and the sample points is in the interval of this xi minus 1 xi. So based on that definitions, okay, I think this the important one is this one. Okay. The whole thing here, okay, the definitions. So the integration from a to b of our fx dx is limit as n approach infinity of our sum of our fx, the sample point delta x. Okay, this is just to make we already discussed this before, but this is the more clearer what we are dealing with. Okay, and of course, if you would write this whole definitions, you need to make sure that the limit, our assumptions, the limit exists. The limit is exists and have the exact value. So give the sum value of all possible choice of the sample points we are choosing from the function. Okay. So in conclusions, the function will be integrable on the a-b interval. Okay. I think this one you need to make sure that, okay, provided the limit of this sum exists, gives some value, then we can say this integration is correct. Okay. Okay. Um, I think some notes to end our course. Notes for sigma or sum. I believe you have learned before, but let me write just the property of sum. Okay. So if you have sum from 1 to n of 1, this is actually n. Okay. If you have sum of 1 to n of I, this will be n plus 1 over 2. Okay. This is, I believe, this is called the series. Okay. And then if you have sum I squared, this will be n plus 1, 2n plus 1, divide all by 6. And if sigma from 1 to n, and you have cube, it's the n plus 1 over 2 squared. And you have sigma. If you have c as a constant, this is, you can rewrite the sum as like that. Let me resize this to make sure. And if you have the and also for the minus, okay. Okay, so basically what these notes mean, if you want to integrate any functions, okay, based on our definition of integrations with sum, if your functions include like the squared, cube, having a constant, like we are doing the derivative when we derive, but we are not sure how to derive, we are going back to the limit definitions, right? So this is actually similar. So if we want to derive functions here, and we are not sure how to derive these functions, we can go to make approximation through the sum, and the notes here will help you to get what kind of approximations you will have. Okay, I think you really learned before, right? Some of this, okay? Because it takes a while to prove this I squared to here. I think this one is easy. These two is, these two need some notes. Okay. Okay. Okay, let's just end until here, until the definition of the definite integral. Okay. And as a reminder, if you have problem with the quiz, either the maybe some mistake I made when calculating your total point, or maybe you have some answers that haven't counted as a point, please come to me. Okay. So I will end our course until these definitions. Okay.